let's jump right away into the ideal diode analysis. All right, so we stopped here and we spoke about ideal diode analysis. This is a very quick and easy technique to apply to any kind of circuits, especially if you have multiple diodes in the same circuit. Okay, so in the forward bias, we say when the voltage is slightly greater than 0, diode is forward biased. We say the diode is on, replace it with a short circuit. And hence, if it's a short circuit, we are modeling the diode as a short circuit in the forward bias. So the voltage across the diode would be equal to 0, right? Voltage would be 0. And current, that would mean current is greater than or equal to 0, right? It's forward bias and it's just free flowing. And in reverse bias, it's completely off. It's completely off. It's an ideal diode, meaning it's an infinite resistance, open circuit. Okay, so we replace it with the open circuit and current would be completely equal to 0. VD would be equal to the minus voltage across the anode and the cathode, right? The cathode must be higher potential than the anode. Otherwise, the diode would not be reverse bias. So those are the two things. ID would be equal to 0 and VD would be negative, right? VD would be negative. When we state VD, always understand that we always take anode as the positive reference. Okay? Diode voltage is always measured at the anode with your reference at the cathode. Anode is always the positive reference. So VD is negative means anode is at a negative potential with respect to the cathode. This technique is also referred to as a piecewise linear model. How many of you have heard of piecewise linear analysis? Hopefully, somewhere in math, even in circuits too, perhaps. So if you have a waveform or a signal or any kind of system for that matter that is nonlinear, you can break it up into smaller pieces where each piece will be linear. So in this case, if we break up our device performance right here, this is forward bias, this is reverse bias. If we break up this characteristic between forward and reverse, we can state that the forward bias characteristic or the forward bias device performance is linear, as well as the reverse bias, which is also linear, right? So we'd have the forward bias characteristics, which looks like this, straight line. Then you have the reverse bias. Reverse bias is also a straight line. So we break it up into multiple pieces, hence piecewise linear. So it's also known as the piecewise linear model. Okay. All right, so let's apply to the example circuit that we presented in the previous slide. This one, right? We have one diode. Let's first assume that the diode is forward bias. If the diode is forward bias, or is connected in the forward bias, we can state, or we can replace it with a short circuit. That's the diode. We are saying the diode is on, D on. And if it's on, it is conducting current. meaning ID must have some positive value. So ID should be greater than 0. ID must be greater than 0. So an ideal diode, there's only two possible states, on or off. If it's on, ID has to flow through. If it's off, ID is equal to 0. V is negative. So once you assume a state, then you analyze the circuit, you redraw the circuit according to your assumptions. Then you analyze the circuit, form circuit analysis techniques, any technique that you would like to use, and then see whether your assumption is true or not. In this case, V, voltage must be 0 and ID must be positive. So if we analyze this circuit right here, simple circuit with a voltage source and a resistor, apply Ohm's law, and we obtain ID is equal to 10 volts minus 0 volts divided by 10,000, which gives me 1 milliamp. And 1 milliamp is a positive value. It's greater than 0. Thus, my assumption is verified and it's valid. So ID is positive. Therefore, assumption is valid. All right, let's take a pause, write it down, think over it. Let me know if you have any questions. I'm impressed. There's almost half the class is present, and then a few students online. Usually I'm down to less than 10. But this because that's also because it's like non-E major classes, especially for the 8 o'clock class. It's kind of about the same. Yeah. All right, any questions? Okay, then let's look at what if it's like reverse bias? What if the diode was connected in the opposite direction? Meaning the circuit itself is now changed. Oh, completely off. Okay. This, of course, is very easy or straightforward to see. You have the cathode, the anode connected negative and the supply. So we would assume D is off. So my circuit becomes like this. And of course, I'm stating because it's reverse bias, this voltage must be higher than this. Diode VD, of course, if you're stating VD, anode is here, cathode is up top. So VD must have a negative value in order for my assumption to hold true. Right? VD must have a negative value. If I assume my diode is off, VD must have a negative value. And of course, this is rather straightforward. Open circuit, no current flowing through, so I is equal to 0. So that's one point that is valid. ID must be equal to 0, so it is 0. And then, of course, one single source, apply KVL, we do obtain VD is equal to minus 10 volts. Minus 10 volts. Thus, our assumption is verified and is valid. Okay. So let's take a pause, then I'll recap. Make sense? Technique. So again, ideal diode model. Make an assumption at the beginning of the state of the diode, either on or off. If it's on, then current must be positive. If it's off, then voltage must be negative. You perform your analysis using any circuit analysis technique that fits the model, fits the circuit, and then verify whether your assumptions are true or not. If it's true, great, you're done. If it's not true, then you go back and you change the state, and then you analyze the circuit all over again. That is what you'd be doing as a practicing or working engineer. Repeat analysis. This is, of course, a straightforward circuit, only one diode, but you have circuits with multiple diodes. So that quickly raises the number of possible states. It's like binary, it's binary math. And so if you have n number of diodes, each diode has two possible states. So total possible states is equal to 2 raised to n. So one diode, you can make one assumption incorrect, and you can redo it one more time, so just twice. But if it's two diodes, you now have four possible states, four possible assumptions to make, and then four separate analyses that you could try. 3 diodes, 8 analyses. 4 diodes, 16 analyses. And so it would require a very educated guess at the beginning of your analysis, right? You make certain assumptions in a circuit, but those assumptions are based on logic and rules, right? If the anode of a diode is connected to a positive voltage and the cathode is kind of lower, logic dictates or rules dictate that the diode must be on. So your assumption should be that the diode state is on, for example. Make sense, right? So again, iterative analysis, you just have to repeat the analysis based on certain assumptions you make at the beginning. Those assumptions are based on logic and rules. Yes.
Parallel or theory, because like if it's parallel, in one because if you have a short, right, everything else doesn't matter.
So if you parallel as in whether your diode is in parallel with another diode, and the answer is yes. Because if there are two diodes, two or more diodes connected in parallel, they are sharing the same voltage. So if you assume one of them is on, then everything should be on. If one of them is off, everything would be off because they are the same two nodes. So the same state would apply to all of them. Yeah, and it is possible in real life to do that, because you would, if you wish to increase the current carrying capacity of the circuit, we would connect multiple diodes in parallel. If you wish to increase the voltage, inverse voltage capacity of a circuit, we would connect diodes in series. So it is a real life possibility where you have multiple diodes in parallel and multiple diodes in series. Yes.
Do you think the basic solving problem like method is we make assumptions in the beginning, work through it, and then we have to check these assumptions at the end to see if they're valid?
Yep.
and if they're not valid, then we go back and try.
Yep. It's like a flow chart. It's like you make an assumption, yes, no. And then if it's yes, you keep going down. Then if it's no, then you go back and then you repeat. Yes.
So you said that you get an increase in voltage if the diode is
No, yes. Yeah. So if you think about it, if you have one diode and you're forward biasing the diode, you would need, let's see, 0.6 volts to turn it on. If you have two diodes in series, now you need 1.2 volts to turn it on. Three diodes in series, you need 1.8 volts to turn it on. In the reverse bias, let's say, for example, if one diode can handle 50 volts in the reverse bias, meaning let's say you are connecting your surge protector. You don't want the voltage to go beyond a certain limit. One diode can handle up to 50 volts in the reverse. You put in two diodes, now your range is expanded to 100 volts. So that comes later. Yeah. Good discussion. And we will see just at the end of this, I don't know if you'll have time to get into it today, but there's a 3-diode example where we analyze a circuit with 3 diodes and we'll assume a state on or off and analyze it that way. And so on purpose, we'll make assumptions, one of which is not true. And then, you can see how long it takes to get it solved. And then we look at bridge rectifiers and full wave rectifiers where we use 2 diodes and 4 diodes. So there you will see, 2 diodes connected in series in that circuit. Okay. Let's see. Any other questions? Okay. So then the next model is the constant voltage drop model. It is exactly the same as, well, I would say exactly the same. It is similar to the ideal diode model, except we add on the practical effects of requiring a 0.6 volts to turn the diode on. So we incorporate or we add in the built-in potential that is required, the threshold voltage that is required to overcome the built-in protection to turn on the diode. Turn on voltage to ideal model. Okay, we add the turn on voltage to the ideal model. And typically we would say, depending on the diode, of course. If the germanium diode, you would take 0.2 volts. If it's a silicon diode, you would take 0.6, 0.7. It would be up to you as an engineer to decide what you would wish to use, right? Depending on what diodes you have available to you. And so silicon, let's say we take 0.6 volts. Germanium, we would take 0.2 volts. If it's gallium arsenide, if it's an LED, what do we take? 1.2, 1.3 volts. We went up to 2 volts in the lab, but it started turning on at 1.2 volts. Yeah. Anyway, so depending on what diode you have in your circuit, you would choose that voltage drop. But again, we are adding it on to the ideal diode model. So we are not changing the linear relationship, right? We've still broken it down into 2 linear pieces, forward bias, and then, forward bias is a vertical line, reverse bias is a flat horizontal line. All we are doing is we are stating that 0.6 volts is required to turn it on. So we are shifting the characteristics to the right. Okay. And so we are adding in a basically voltage source that needs to be incorporated into that model, which is added on right here. So that provides a voltage drop of 0.6 volts, hence the name of this model, constant voltage drop model. It's not non-linear. We're simply stating it's 0.6 volts. So once the voltage across the terminals between the anode and the far right here goes above 0.6 volts, the diode is forward bias replaced with a short circuit. Exactly the same thing as what we did for the ideal diode, except we have to build in 0.6 volts, hence constant voltage drop. So in the forward bias, it is modeled as a voltage source with a value of V on. And then in the reverse bias, of course, it is the same as an open circuit. So this is reverse bias. That makes sense? So in the previous example, we had the diode that was forward bias. So if we replace that with a constant voltage drop model, we could draw the circuit like this. So instead of a short circuit, we now have a voltage source that is required. The anode positive and cathode negative. So plus minus 0.6. This was 10K, 10 volts. Everything else remains the same. The assumptions, the steps that we did, make an assumption at the beginning. The diode is on, diode is off, calculate ID, calculate VD, everything else stays the same. The only difference is in forward bias, for the constant voltage drop model, we add in a voltage source of value VD. V on. Yes.
The voltage source just replaces when we short it.
In forward bias. Yes. So the question being asked is about forward bias. And the answer is yes. Just replace the voltage source of turn on voltage. That's the only difference. And we can see that, right? It's here, reverse bias, open circuit, right? This is reverse bias. This is forward bias. Reverse bias is still open circuit. And forward biases, it just takes in the practical effects of the built-in potential. So here, if I wanted to find ID, equation would still be the same. I would apply node voltage, node analysis, 10 minus 0.6 divided by 10,000. So 9.4 divided by 10,000. So 0.94 milliamps. 0.94 milliamps. Which, if you check back your notes on the load line analysis, was 0.94 milliamps. So right there, 0.94. So ideal diode is a very quick and easy analysis. I wouldn't say easy, but quick analysis, right? On, off, zero or reverse bias. But we add in practical effects with the voltage drop, we can get an even more accurate prediction of our values. All right, 10-second pause. Let me know if you have any questions. Yes.
Say you assume wrong on the voltage, and so that when she gets.
Well, no, wait. So if our assumption is incorrect, So the question being asked is, what if our assumption is incorrect? Let's say you obtain a negative value for the current, or maybe 0 value for ID. That means, so then our assumption, yeah, then it's not consistent with the assumption we made earlier, meaning our diode is not on, it's actually off. So then we go back and analyze it, or diode is off. When the diode is off, we are not reversing the voltage source. We simply replace it with an open circuit. Yeah. Was there a follow-up to that question? Okay. So again, the two states, keep in mind, if it's on, either a short circuit or 0.6 volts. If it's off, it's always an open circuit. Okay, it's always an open circuit. Yes.
So why would you ever do the ideal diode model over the constant voltage drop model if this is more accurate results and it's kind of similar already?
That's a very good question. So the question being asked is, why would we use ideal diode model and not the constant voltage drop model? The answer would be when you want it to be quick. So if you have multiple diodes in a circuit, and all we need, and it also depends on what outcome we need, right? If we don't need a specific voltage or a specific current value, we just need to know whether, let's say, the end of the circuit switch is open, switch is closed, something like that perhaps. Then we just do ideal diode model. Just say on, off, on, off, on, off, and then outputs most likely on, or outputs most likely off. But then if we need a specific voltage or current, then we would perform a more better analysis. True, true. The point being made is, if it's a higher voltage, then the constant voltage drop would not actually matter. Yeah. And we will see that in the example. But before we get to that example, we'll do the last one here is the mathematical model. So mathematical model is basically the equations that we have used, right, so far. The standard diode equation, IS times e raised to VD over VT minus 1. We would use that. And then the diode voltage equation directly from the diode equation. So if you want to do that, we'll take our circuit. Right, I'm going to redraw it out here again. This was our original circuit. This is VD. And this current is ID. The current is the same, so it doesn't really matter. 10 kilo ohms and 10 volts, right? So this is our original circuit. Now we want to we found the value of the diode voltage and the diode current using load line graphical analysis. We found it using the ideal diode model, the constant voltage source model. And we see a very good alignment between load line analysis and the constant voltage drop model, right? Now we will see how we can purely solve it just using the diode equation, right? So the diode equation is, standard equation, of course, is ID times IS, sorry, equal to IS times e raised to VD over VT minus 1. If the non-linearity factor is not given, in most cases, it's never given unless it's a specialized application, n. The value of n, always assume it to be 1, okay? So if n is not given, always assume it to be 1. In this case, it's given to us, but it's still, the same. Whenever possible, that's all engineering is. We always make assumptions based on rules, based on logic, and we try and solve the problem, and then we see if it works or not. If it works, great. If it doesn't work, we go back to the beginning, we change one variable in assumption, and then do it all over again. That's what we do. So if I was to write an expression for the current ID as part of the circuit, We already did that. This is the standard diode equation, of course. ID from the circuit here is simply the voltage source, 10 volts, minus VD over 10,000. Right? Minus VD over 10,000. That would be our equation from the circuit. So again, remember, we have the standard equation for the device. So we have the device equations, ID and VD, just for the device. That's different. But the ID that we have here is basically the current that's actually flowing through the circuit itself. Okay, through the circuit itself. And then, of course, here I can write VD is, I will get rid of the 1 right here, we'll ignore it because the value of that 1 is going to be negligible compared to like a diode voltage or the other quantities in there. And so I can write this is VT times log of VT times, so log ID over S. Okay. So now we have our standard device equations. We have the equation of the current from the circuit. We can either plug VD into that equation or you can plug ID into the other equation, either ways. What we are trying to obtain is a equation that is based on the external circuit. Okay, the entire external circuit. So I can plug, I can either plug ID from here into here, or I can plug VD into here. Either ways. Does that make sense? Right? We are two unknown variables. We have two unknown variables. We need to eliminate at least one. Right? Not at least one. We have to eliminate one. So we get an equation in terms of only one variable. And that's what we're trying to do. So if we plug it in, we can write, if we plug this in here, we can write VD is equal to VT times log of, and this is going to be ID. So 10 minus VD divided by 10,000 IS. Okay. So, right, we have simply plugged ID into the diode voltage equation. So now we have a expression that is solely comprised of one single variable. Yet, we cannot actually solve it. There is no closed form answer for this equation. It's a transcendental variable, log e raised to trigonometric identity is a transcendental equation. So there is no closed form single solution for this. So we have to perform an iterative analysis, kind of similar to that flowchart thing. We pick a value for VD, we solve it, we input it in this equation. So we perform an iterative analysis. Because we cannot directly solve this equation. And this iterative analysis, we choose a starting point for a value of VD. And calculate VD. So we have, so here, let me walk through this. We have an equation for a variable. VD is equal to something, right? But that equation also has the same variable VD. So we choose a starting point for VD, we enter it into the right side of the equation. If we choose as a starting point for, let's say, if we choose 0, let's say VD is equal to 0, we plug it into the right side of the equation. We solve it. The final answer is VD equal to 0. Do we obtain VD equal to 0 or not? Meaning, choose VD equal to 0, solve the equation. Do we obtain VD equal to 0? If we obtain VD equal to 0, then yes, our assumption is correct. If not, we go back and choose a different value for VD. We again solve this equation and then see what the answer is for VD. Am I making sense? Yes.
Guessing values of VD to try and get it equal to.
Bingo.
Is there any way to make that process more like?
Yes. So the point being made is, are we simply guessing here? Yes, we are. We are just throwing stuff at the wall, seeing what sticks. But there is there's a little bit of procedure to it. It's not just madness. So this here is in Excel, but it's possible to do software computation using MATLAB or any kind of software. And of course, in the days gone by, we had to do this manually, right? So it is possible to do it manually, but it converges very quickly. You can see here, this is just done in a spreadsheet, right? Again, so it's not like the most elegant way, but it's very effective. Once you program the equation in there, so this is VD, V minus VD. This is the equation. This is right here. And then after that is the log, and then log times VT. So as a starting point, if I chose VD as 0, I obtain an answer for VD as 0.594. Then I could take the 0.594 and do a second iteration. But this was just an example to show, so instead of going from 0 to 0.594, I know my diode voltage has to be between 0.6 and 0.7, right? Diode voltage must be between 0.6 and 0.7. And so I chose 0.65. If I choose 0.65, I get an answer of 0.592. When I plug that back into the next iteration, I obtain an answer of 0.592. See, it's converging very quickly within like 3 steps, 2 steps actually. And then I plug that answer back in here. I again obtain 0.592. And then after that, it's exactly the same for like up to 6 decimal points. So it converges very quickly. So once you have the equation program, that spreadsheet or any software you want, you simply pick a starting point. If you wish to pick 0, you can pick a 0. So in that case, I would have plugged in 0.594 into my second step. Might have taken maybe 1 step extra, maybe 2 steps extra. But again, it's software, just drag it down, like within like a second, you get the answer. And, dragged it down like 3 steps, 0.592, 491, 491, 491. It converged very quickly. And so then I can confidently state, if I plug this answer in here, I still obtain the exact same answer, meaning I chose a value for VD, I performed my solution. I calculated the value, and my solution is exactly the same as my assumption. So my assumption is valid. And so that's where I would end, and I would state, okay, same answer as my assumption. So this are my assumptions, and these are my calculations. When your calculation matches up with your assumption, that's where you stop. That's where we say our model has converged. And truly, we don't even have to go all the way to like 6, 7 digits. 0.594, 592, and 592. Within 3 steps, it has converged. Yes. Oh, yeah, 0.65 was actually the starting point, but I just chose 0 just to show an example. 0.65 is because it's halfway between 0.6 and 0.7. And so if it's a silicon diode, my starting point, my diode voltage, if I'm assuming it to be on, would be somewhere between 0.6 and 0.7. So I chose 0.65 and took it from there. But the 0 was chosen just to illustrate that you could start with 0 and still perhaps obtain some value. Now, as you go along, you get more experience. You may come across a problem where 0 may not be correct. Like you would enter a 0 and your final answer might be 0. And if you enter like 0.6, it'll be something else. So we don't know. You only would obtain that with experience. Okay. What I will do is after class, once I go back to my office, I'm going to add a couple more extra steps in there, see how long it takes to go from 0.594 to our final value. Okay. So it's 0.592, and that's the diode voltage we obtained from the mathematical model. If we compare all values using the 4 techniques, which is right here. From the load line analysis, remember we made the assumption eyeballing it. And I said it's about 0.95, but we could say it's between 0.94 and 0.95. So let's say 0.94. So we took 0.94. Mathematically, if I, using the 0.592, if I calculate my diode current, I get 0.941. With the ideal diode model, it's obviously either on or off. So it's 0 or 1. So we got 1 milliamp, right? And the diode voltage was 0. And then the constant voltage drop, give a more accurate value. So 0.6 and 0.94. So that's the comparison of all the 4 different analysis techniques using 4 different models. Okay. As I stated in the first day of class, first week of class, the entire electronics analysis is about just making assumptions. We'll have multiple models. You as an engineer have to decide which model you would like to choose for your particular application, right? And so that's what this is. Now, it's 9 o'clock. So if you have to leave, you can leave. I want to just go over rectifier circuits. Okay, so I just want to introduce rectifier circuits briefly. Any questions before I move on? Any questions from anyone? Okay, so that's the multiple diodes circuit. This is going to take that period. So I don't know if I want to do this now or just introduce. Let me just introduce rectifier circuits. Let's do that. So rectifier circuits are basically converters from AC to DC. Okay, so they take the AC power outlets and convert it into DC. And it's very interesting. All electrical power generation and distribution is done in AC. And credit, usually it's a work of like lots of researchers, but largely the credit is given to Tesla because he took unsolvable problems and figured out a way to actually actually implement it in real life. So there were like Hungarian researchers who actually had the first working model of a transformer. And transformer, not the Michael Bay transformers, these ones either step up or step down your AC voltages, right? So AC transformers, once we had a working practical model of a AC transformer, it was very easy to use it to step up a voltage or step down the voltage. And the reason it was very important is for AC power transmission. Okay, AC power transmission. So when AC power is generated at the power station, might be a few tens of a volts, few hundreds of a volts. It is quickly stepped up to thousands of volts. So when you want to send your electrical power over long distances, a transmission line, which might be, pure conductor, will have some resistance. So even a transmission line that is a pure conductor will have resistance, because again, resistance is rho L over A, directly proportional to the length of your conductor. So when your conductor is like miles long, sometimes hundreds of miles long, even that tiny resistance has a big effect. And so when you're transmitting power over long distances, there is power loss in the transmission lines due to that resistance. So when you have power loss, electrical power, P is equal to IV, directly proportional to voltage and current. Also, in terms of the resistance, it's I squared times R. So the higher your resistance and the higher your current, the more your losses, exponentially in that sense, right? It's I square R losses. So in order to reduce those, you want to transmit voltage as high as possible. So you transmit voltage at like tens of thousands of volts, okay? Tens of thousands of volts. Once it reaches, near the destination, near the consumer, where the consumers are, step down using transformers. Again, you would have seen those electrical panels around campus behind like enclosed structures, let's say danger high voltages, or if you've noticed, you have electrical poles and you have cylinders wrapped around electrical poles. Those are transformers that step it down. So everywhere we go, it's all AC. But on the flip side, almost every device that we use in everyday life is all DC. Everything is DC. Monitors, displays, projectors, your cell phones, mobile devices, laptops, televisions, every electronic device that you use is primarily DC. DC is very convenient. We don't have, with the AC, we have fluctuations. We don't have to worry about those. We know we need a constant voltage. And so there comes in our humble diode. Nothing would actually work in this world if we didn't have the diode. It's a very important piece on which everything works or everything runs. A diode is a one-way street. It's a one-way device. It only conveys or conducts electricity in one direction. And so if you have an alternating signal, AC, which conducts in both positive and negative directions, you apply it to a diode, diode will only turn on in one direction, only conducts current in one direction, and hence we can convert AC to DC very easily. How many of you are familiar with the term wall wart? Wall wart. Wall wart, not mart, wall wart. So they're basically the chargers that you plug into the wall. Okay. The bricks, exactly. But now it's of course changed with the advancement in technology, but they used to be small transformers, and small transformers, even when I say small, it's like the size of my fist. So small transformers that would take the power, electrical voltage from 110, 120 volts and bring it down to like 10 volts or 15 volts, depending on the requirements. And then you take this 10, 15 volts AC and you apply it to a diode circuit. The diode would rectify it to DC and then filter it out, and you get 10 volts DC at the output. And because they were like, well, as we said, kind of like the comment is an insult. So they came to be known derogatorily as wall warts, because everywhere you would go, you would see those plugged into the walls for every single appliance. I can't get my hands on one right now, but I believe there are some transformers that are being used in one of the projects. So I'm going to bring it along for next class. Anyway, we'll end class here today, and we'll see you all on Friday. It's the exact same thing. It's a DC power supply. Well, it looks like a brick. That's why they call it a brick. No, so there's a lot of other things in there. So first we have, and it's very interesting how they do it. Now they don't use a transformer to step it down. They use a high voltage diode to simply convert 110 volts, 120 volts directly to DC first. Then they convert that DC, so they step down that DC to a lower level. And then they convert that one to AC using a high frequency transformer. And they convert it back into DC. And that's why we have our like lightweight chargers that we plug into the wall, like the small cell phone chargers that we use. That's why they are so small and lightweight. It's because the size of the transformer is very tiny. If you have an extra one lying around that you don't use, crack it open. Take a look. I'll crack one open and see if I can find one. I'll bring it. But the brick, the answer to your original question, the brick is because there's tons of other things in there. It's actually called a switching mode power supply, SMP, switch mode power supply, SMPS. There has to be voltage regulation, filtering capacity. You don't want it to go over voltage. If it goes over voltage, it shouldn't burn out. So there's a lot of things in there. That, yeah. Plus, it's high wattage, power handling. Yeah. No, it's on there. You're an electrical engineer. No, it gives you no. Yeah, it's at least 100 watts.
Hopefully.
I'll tell you, it's at least 100.
There. Should be on
180. No, 240. I have the exact same one. My laptop is a brick, like real brick. Oh, I think we